Hey everyone, glad to see you. Welcome to the AI Sanctorum. In this video lecture series, we'll be going over some of the fundamentals of AI. Specifically, the way I wanted to work this series is by first making a video lecture purely based on the theory aspect of the algorithm, and then following will be the code. So let's get started. Awesome, so let's jump right in. This is the very first lecture in the series, and we're going to be going over the naive Bayes algorithm. If you haven't already heard of this, this is one of the most fundamental algorithms in AI. And as you might have already guessed, it is based on Bayes' theorem. Now, for those of you that have already taken some sort of statistics or probability course, have probably already seen this formula before. This is Bayes' theorem and basically allows us to solve for the probability of something happening given information that we already know. So let's take a deeper look into this equation. So if we say start at the left-hand side of the equation, we see this PA line B. Now, all this means is the probability of some event A happening given some event B. That's what writing this means. It's just a probability. Now, similarly, this is the same on the right-hand side. The only difference is that here we see this PB line A, and this is read as the probability of some event B happening given some event A. Now, you also see these two things over here, that there is a P of A and a P of B. Now, these are independent probabilities, or in other words, they don't depend on some other event happening, right? So you see in these two things right here, it's the probability of event A given B, or the probability of B given A. But in this case, there's no or there's no event based on something. It's just probability of A and the probability of B. So let's take an example, say, of a coin or two coins, right? So let's say the first coin is your event A, or the flip of the first coin is event A, and the flip of the second coin is event B, or vice versa, right? So the first coin is event B and the second coin is event A. And I asked you basically, what is the probability that your second coin is going to land on heads, given the fact that I told you the first coin landed on, say, heads as well. And so in order to solve for that, all you'd have to do is apply the same equation, right? So we would first look probability of B given A. So this is the probability of that first coin flip given the probability, or that second coin flip. Now, in this case, this is a very simple example because coins are totally independent on each other, right? They're not dependent on each other. And so no matter how you flip the coin or in whichever order, the probability of it landing heads is always going to be 1/2. And so what happens is that you get the probability of event B given event A will equal to 1/2, because it's just saying the probability of that first coin being a heads given the fact that the probability of the second coin is, let's say, a heads. Well, that's still going to be just 1/2. Now this is times the probability of A, or probability of event A. So this is just the probability of that second coin being a heads, which once again is 1/2. Probability of B, which is the probability of the first coin being heads, is also 1/2. So you get 1/2 times 1/2 divided by 1/2, which is just 1/2. And so thus we can solve for the probability of that second coin flip being heads, given the fact that the first coin is also heads, is still going to remain 1/2. We can also take a breakfast example. Now, I guess this is a little bit more abstract, but it still gets the point across. So let's say that I asked you, what is the chance that you drink orange juice given the fact that you had already eaten bread? Well, in order to solve this, we would use the same equation. And so once again, let's kind of look at this, right? So you have your event A, which is orange juice, and event B, which is eating bread. So the left-hand side of this equation can be read the probability of event A given event B, or the probability of drinking orange juice given the fact that you had already eaten toast. Now, this can be applied as well with this equation, and we just do the same thing as we did before. So you have the probability of event B given event A. So this is just saying the probability of you eating toast after drinking juice times the probability of event A, which is just the probability of drinking juice, and all over the probability of B, which is just the probability of eating toast. And so let's say that we had the numbers for these, we would be able to solve the probability of drinking juice after eating toast. But you might be wondering, and correctly wondering, how all of this applies to machine learning. Well, let's take a look at a classification example. Right, so this is just a generalized classification problem, no significant numbers or anything, but let's take a look at this. So what these rows are saying is that we have the three different objects. So row 1 is object 1, row 2 is object 2, and row 3 is object 3. And these objects have different variables or attributes to them. So you have variable 1 or attribute 1, variable 2 or attribute 2, or variable 3 or attribute 3. And respectively, these values are x1, y1, and z1 for the first object, and so on and so forth for the other objects as well. But you also see this column over here, the classification problem, right? And so what this is saying is that this object, this first object, is part of classification 0. This second object is part of classification 2. And this third object is part of classification 1. And so what we're doing basically is saying, given these three different things, what is the classification for that? That's how the machine learning plays into this, right? We're trying to predict, given these three different values, what type of classification is this object? Sound familiar? Well, it's exactly what we've been doing. Given these probabilities, we can solve, or given these values for probabilities, we can solve for the probability we want, right? So in this case, this event A will be the classification, whereas the event B will just be the values of these different attributes, or the probabilities of these values happening, right? And so this is exactly what we've been doing before, and that's how we can apply Bayes' theorem to a classification problem in machine learning, right? So let's take a deeper look into this. Well, in order to do that, oh, and as you saw here, event A and event B would play like this. So in order to do that, let's see this iris dataset. Now, you might have already heard of this. It's a famous dataset for classification and was initially created by R.A. Fisher. And basically what it's doing is it's describing the iris flower. And so what they do is they have 4 attributes for each flower. And what an attribute is in this case is just say, like the petal or the color, or the size of flower, but in this case it has 4 specific attributes of these iris flowers. And what its classifications are, well, there are 3 different classes of these flowers, and you'll see these different attributes and classes on the next slide. So let's put some of these examples on a table. So you see these example 1, example 2, and example 3. All these are just representing as flowers 1, 2, and 3. And you see over here, instead of variables 1, 2, 3, I have exact attributes, or attributes of a flower. So you see the sepal length, the sepal width, the petal length, and the petal width, right? So for each flower, or let's take the first flower, right? So in the first flower, you have a sepal length of 5.1, a sepal width of 3.5, a petal length of 1.4, and a petal width of 0.2. Now this is flower 1. And the class it's given is Iris setosa. This is a classification of the iris flower. So in the iris dataset, you're given 3 different classifications: the Iris setosa, the Iris versicolor, or the Iris virginica. And all the flowers in the dataset fall under one of these 3 categories. Now, what we can see here is that the first flower corresponds to Iris setosa, the second flower corresponds to Iris versicolor, and the third flower corresponds to Iris virginica. And what that's basically saying is, given these 4 different values, I can predict what class this is going to be in, right? So with these 4 values, it's going to be a setosa. With these 4 values, it's going to be a versicolor. With these 4 values, it's going to be a virginica. And so in order to solve for which class it's going to be, all we would have to do is apply that same equation that we saw earlier, where you have event B, which is basically the probability of these things happening, these attributes occurring, and event A, which is essentially the probability of the class. But you might immediately notice something a little different, right? So in the earlier examples, what we saw was one event directly corresponded to a second event. But what's happening here is that there are four different attributes that we're considering. We're not considering one different attribute, right? So let's say the coin example. So in the first example, it's either heads or tails for that first coin. But in this case, we have the sepal length width or the petal length and width, which are four different attributes. So how exactly would we consider this in terms of our equation? Well, it's pretty simple. All we have to do is switch up the equation a slight bit. Now this might look daunting at first sight, but it's essentially saying the same exact thing. So let's look at the left-hand side. We have the probability of A given these different events, B1 to Bn. Now what this B1 to Bn, is just the probabilities of those different attributes occurring. So if we look back here, that's the probabilities of the sepal length, sepal width, and petal width. Right, so these attributes are given. So what this is saying once again is the probability of some class occurring given these different attributes. Now what this is going to equal to is this thing right here. Now this symbol, if you don't know, is basically just very similar to the summation symbol, but instead of adding things or summing things together, you're multiplying each of the values. Now this is going to be P Bi given A. So what this is saying is the probability of that attribute given this class. And I'd also like to point out one more thing, that this value of n right here, this value of n, this is just the number of attributes, right? So in this case, n would be 4 in the case of the iris dataset. Awesome. So over here we see that there's this P of A. Now once again, that's just the probability of it being some class, meaning the Setosa, versicolor, or virginica. And down here we see this P B1 to Bn, which is the probability of these attributes occurring. But one thing to also note is that in the iris dataset, there's not one class. There are multiple classes happening, right? So in the orange juice toast example, it's either what's the probability that you drank orange juice or you didn't drink it, right? And so that's just one thing. It's just a yes or no to that one thing. But in this case, you can have three different classes, right? So there's the Setosa, the versicolor, and the virginica. So this is only one equation, but how would I figure out of those three classes which one these attributes correspond to, which one the flower corresponds to? Well, it's very simple. All we have to do is just take apply this function to all the classes and choose the classification with the highest probability, or take the argmax with respect to event A. So all that means is we have these three different classes, right? And so what we do is we apply this equation to all three of these different classes, so the Setosa, versicolor, virginica, and we plug in each one as event A. Now we take the attributes to be the same each time, and we solve for this value right here, this P A given B1 to Bn. And basically what we're doing is we choose the value that's the highest, and we take that event A, right? So now I kind of want to bring back to the table because I think it makes a little bit more sense. So let's take the first flower, for example, right? So the first flower has these different attributes to it, and it's predicted to be an iris setosa, right? So what it's doing essentially is it's plugging these values as your B1 to Bn, and then it's outputting this as your event A. So what we're doing here is we take these four attributes initially, we take those four attributes and we plug them into this B1 to Bn. Then what we do is we take three different classes, the Setosa, versicolor, virginica, and plug them into this event A. And we solve for this all three times. Now let's say in this case, we get the iris setosa to be having a probability of say 0.7, the iris versicolor when event A to be a probability of 0.3, and maybe virginica 0.2, something random, right? But what we see is that the setosa has the highest probability. It's at 0.7. And so what we do is, because it has the highest probability, we can predict that it has the highest chance of being a setosa. And so that's why we categorize or classify our first flower as a setosa. And we do the same procedure for the other two flowers, for versicolor and virginica. And we choose these three different classes for these three different flowers. And so that kind of concludes the theory behind naive Bayes. I'll be posting another video soon on the actual code behind this iris dataset to kind of give an example of what behind the scenes is going on. I hope that kind of clears some things up if need be. Also, if you really like this lecture series, make sure to subscribe. I'll be posting hopefully every week, and I can't wait to see you next time. Thank you so much.